Welcome to a beautiful Friday. We are going to go ahead and get started. At this point in our day, you do not need any technology out. You may need a calculator at some point in the next few minutes, but not right now. And you definitely don't need a computer out, and you definitely don't need a phone out. But you will need some notes and some things to write on. And why don't you also send somebody from your table up to get a whiteboard and a marker and an eraser? All right. So, my friends, as we get started today, I want to remind you of where we ended yesterday. It's as if we never left. No, we did. But we just want to jump back in right where our brains were yesterday afternoon. I reminded you yesterday that we started talking about Newton's first and second law again, right? We know Newton's first and second law, no problem, when we're talking about translational motion. If F net is 0, A is 0. If F net is not 0, A is not 0. Boom, you're done, okay? A is equal to F net over M. And this thing here, this mass, we've just kind of talked about it and said, oh, it's fine, right? But really, if you think about it from kind of a very fundamental perspective, not from the perspective of an AP physics student, but from the perspective of somebody who's like really trying to understand this like before all of the groundwork had been laid, okay? Kind of going back to, do you remember forever ago when I was describing like pushing a boulder, right? The boulder has a lot of what we now call mass. And as a result, if you were going to anthropomorphize the boulder, do you know what that means? Like make it have human characteristics. A really, really large boulder doesn't want to go anywhere. Are you with me there? Okay? It's got a lot of mass. It's not going to go anywhere unless you give it a really big force. Okay? Whereas a really like gigantic beach ball that's the same size as the boulder, so same size, no problem, all the same stuff. You push that, it's going to go no problem. Because it doesn't have a problem moving, right? That's kind of what mass really means. From a like kind of a very low level, fundamentally different approach, I guess, if you want to say it that way. I want you to keep that in mind as we move over here to the rotation business. So at the end of the day yesterday, we said, oh yeah, we're just going to write this down as kind of the rotational equivalent. So we said, if torque net is 0, then alpha, which is, what does alpha represent? Rotational acceleration equals 0. This is all of that rotational equilibrium stuff that we did, okay? This is those two masses hanging on the meter stick that was on the marker ages ago now. Okay, this is the same thing as when we had the 1 meter stick and the mass sticking out like this. It's in rotational equilibrium, which means it's not going to tip. It's not going to spin. There's no acceleration about an axis. If, on the other hand, this is the second part of the law, right? If the net torque is not 0, then by golly, it is going to spin. And not only is it going to spin, because it could spin at a constant rate, right? If omega was constant, no net torque there. But if the net torque is not 0, then that thing is going to speed up or slow down, okay, as it's spinning. Again, this is all just spinning about an axis, whereas this is all just moving in a straight line. That's the only real difference. So then we said, okay, well, if that's all true, then we've got to have alpha is equal to torque net over something. And we haven't really talked about what the rotational equivalent of mass is, right? So we went through all this little business here to kind of prove this. And this part, like, I'm really happy to go through this with you if you want to see it again. I'm happy to do that. But what I really want you to know, the big takeaway from that, is that unlike when we have translational motion And we're just talking about this mass thing. And this mass is really like, it kind of makes my heart sink a little bit when I say it, but I'm going to say it anyway. It's kind of like the resistance to change, right? It doesn't want to start moving, or it doesn't want to stop, right? If you have a rolling boulder coming at you, like, better to get out of the way than to try and stop it. Because it has a lot of mass, it's going to take a lot of force to get it to stop. Okay? Same kind of idea here, but this thing has the most ridiculous name in the history of all of physics, okay? That often scares people, and I want this to not be a scary day for you, okay? Moment of inertia. You ready for this, Grace? It's going to be great. Yeah. Psyched up? Moment of inertia. All it is quantifying an object's resistance to change in rotational motion, okay? Let's write that down. Did you say that's not scary at all? Oh, it does? Okay, well, we'll talk about it for a while today and it'll be okay. So it's an object's resistance to change. What did I said it really nicely and then I forgot what I said. Object's resistance to change in rotational motion. Or rotation around an axis. Okay. So the funny thing about rotation is that it involves the mass, but what else does it involve? The radius. And sometimes radius, we always associate radius with a circle, right? And that kind of deal. But I want to maybe define radius as the distance from the axis of rotation. Okay. So we can talk about this very theoretically and kind of a funny high level all we want, but I feel like when I was learning this, as my teacher told me this, I'm like, I don't have any idea what that means. But as soon as we started talking about examples, and it helped to solidify it a little bit more. So I'm going to go there right now, okay? And then we can come back to the definition and kind of play with it a little bit more and see how we feel about it, okay? So I want you to imagine, I'm going to put a new page in here real quick. I want you to imagine, at my old school, I had this demo thing, and I don't have it yet. And I, of course, didn't think to order it until yesterday, and but even Amazon is not quite that good to make it happen quite, I guess, or maybe I'm not willing to pay enough to make that happen. So I'm going to have you do a little thinking experiment here. I want you to imagine that you have let's see, how do I want to do this? Sorry. I'm changing my mind here. You have a meter stick with a big mass attached to one end. We probably could just build this, couldn't we? Or just get a hammer. I don't have a hammer. Do you have a hammer? I do have a hammer, I think.
But that's, she made it look like a hammer too.
It's a mallet, actually.
That's a mallet.
It's just a.
It's a mallet for what kind of thing is it?
Diamond.
Diamond, yeah, there you go.
Diamond.
Only diamond, I guess. Iron
Who's
diamond.
you win today?
Yeah.
This person. It's not like the coolest hammer in the world. I don't want to give him,
Ray
but
Harrison, would you win?
he wins props for the day. Okay. Imagine that you have a big stick with a mass attached to it. Let's draw a hammer. That works. That's my attempt at drawing a hammer. How'd I do? It's a thing, right? Lexi's like, wow, don't quit your day job, yo.
It's not bad.
I mean, you know, for a physics teacher, not bad. All right. Henry, don't make fun of my humor. Thanks. I mean,
In concept.
okay. I've told you guys that my husband tells me that, because sometimes I come home, I'm like, I told the best joke today in class. He's like, yeah, and all your students laughed, right? And I'm like, yeah. He's like, yeah, it's because you're grading them. I'm like, no, it's because it was a funny joke, and he never believes me. He really, really thinks that the only reason you guys laugh at me is because you want to get an A. And I really hope that's not true, but, you know, even if it's, right, it is hilarious. That was hilarious too, wasn't it? Anyway, so that's why you're also saying that my hammer is beautiful, right? All right. Okay. So back to whatever reality we're in right now. Tell me about where the center of mass of this hammer is. Where is the center of mass in the middle, right here?
No.
No, they yell. Where is the center of mass? Like way up here, right? Yeah. Okay, so the nice thing about that is that we've got uneven distribution of mass, which means that we've got really, really lovely ways to describe things. So if I was going to swing the hammer, and I was going to try and stop the hammer, which way is it going to be easiest to swing it or stop it? From that way or this way?
That way. This one. Yeah.
This way, right? What? Explain to her what you're talking about.
Yeah, what's
So let me back up for a second. So I'm going to either swing the hammer holding it at the handle, right? Right? Which, I mean, this is how you hammer something.
right?
Yes, we all know this. This is how you hammer something. And why do you hammer it this way as opposed to hammering it this way?
There's more mass.
Draw, right? Yeah, because you can get some force, right, applied. Because you're moving the big, massive part further, right, away from that axis of rotation. You with me there? Axis of rotation down here, boom, right? So once this thing moves, it takes a lot to stop it. Are you with me there? It takes a lot to stop this. Now, if I hold it this way and I go like this, so I hold it from the head part of the hammer and I let it go down, is that gonna like hammer any nail? I mean, maybe into like some jello or something, like nothing interesting. It's not gonna do anything that you actually want. And why is that? Is it pretty easy to stop this?
Yeah.
It's pretty easy to stop this thing. Okay, so let's put that together. What did we just say? This hammer, regardless of if I rotate it about the bottom, about the handle, or about here, it all has the same mass. Are you with me there? Same mass, but a very, very different result, right? If I hammer this way, boom. If I hammer this way, boom, like nothing, right? Okay? Same mass, but we're going to have a very different result. And the reason for that is because of the distribution of the mass, okay? You're going to have a much, well, I'm just going to say different for now, right? Different moment of inertia. That's really what I'm trying to say. From it this way, because all the mass is up here, or most of the mass is there. How are we doing? We okay so far? So that's the kind of like physical thing. Thank you again. I appreciate that. I want to look at a more numerical question now to see if this kind of is sitting okay. So we've got this rod that's made of 3 segments. So it's all the same size, but they're made of different materials. You with me there? So 3 different materials, equal length, different masses. So this one's M, 2M, and 3M. It says the total mass of the rod, well, we can add, but thank you for telling us that it's 6M. Right? Thank you. We got that. Okay. Now, it says, this is going to be some thinking that you need to do. Will the moment of inertia, so let's remind ourselves what that means. The moment of inertia, right, that's mr squared, be greater about the left end or the right end or about the same ends? The word about here is funny. What does about mean?
Almost.
Around, right? So if we rotate it about the left end, that means that I'm going to put my axis of rotation here. Okay? That's going to be like this. Right? Whereas if I do it about the right end, that's going to be putting it over here, or it doesn't matter. Okay? I'm going to let you think about that for a minute. I would encourage you, we're going to do it in a minute anyway, to do some calculations, but go ahead and just think about that from kind of a theoretical perspective. Go ahead and do it. Give it a shot. I am going to encourage you, even if you got it right or think you got it right, to actually do the math here so that we can actually see what's going on. Okay? The moment of inertia about, let's do the left end first. Okay? So we haven't really talked about how to do this. Could you find the moment of inertia of this piece here?
It's on freeze.
Oh, you can't see. You're like, which piece? There you go. That piece, the one with the mass of M.
No.
Can you find the mass of the M piece? Let's do it. I'll help you. Or not the mass, I'm sorry, the moment of inertia.
Oh, I was like,
What letter do we use for moment of inertia? Do we know? Have I told you yet?
R.
I don't know why, but it is.
Double
This
thing,
is so
3L.
intuitive.
I know, right? Stop being intuitive. The moment of inertia of this little piece here, I'll call it A, is going to be the mass of A times the radius squared. Right? What's that? Of that piece, yeah. So let's then we could also write down the moment of inertia of the second piece, right? That's going to be what, it's 2m. Then there's another radius thing in there. We actually, here, let's back up. Let's put some numbers. Who likes numbers?
Hold on.
I'm backing up.
So are we finding it of just that piece?
Nope, I was going to do it that way, but I don't think it's intuitive. So we're going to put numbers in because it'll make you happier. I promise. Trust me, Courtney. How long do you want that rod to be?
6 meters.
Why?
It does not matter. Somebody be loud. I don't care.
6
Why?
meters.
6
6 meters. 6 meters.
Okay.
6 meters.
I'm taking the vote of 6 meters. Now, if you want to do something different, you absolutely can. That's a really, really long. Let's not do 6.
Why?
1 meter.
1 meter.
1 meter is much more reasonable in terms of like actually rotating something. Okay. Shh. Friends, don't fight with me because we gotta go. Shh. A 6 meter long piece, that's like, I don't know, I can't rotate that. You just
have to go to waste in the morning.
You guys are hilarious.
Hi.
And I'm going to say that my M is equal to 1 kilogram. Let's just keep it simple. What's that? Are you sure you're okay? Okay. So, friends, I'm going to stick with 1 here, and I'm going to stick with 1 here. You can do whatever you want because I'm not grading your paper. Like, I don't care. But this is what I'm going to do. So if you want to follow along with me, that's what we're going to do. We're going to find the net torque, or excuse me, the net or the total moment of inertia. Here it comes. I total about the left axis, right? The left end. This is version 1. Does that make sense, Courtney? Do you see what I'm saying?
Yeah.
Okay. So the calculus kid may want to say, all right, I need to find the moment of inertia of this piece and 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 this piece. And you can do that. But we're not going to do that in here. I'm going to find this piece here. Where is the center of mass of this piece here?
Right at the end.
In the middle.
Why would you say that?
Hey. Kindness. Right? Kindness. I just want to make sure that's like a thing, right? So where is the center of mass of this guy?
The center.
Right there. How far away? What's the radius? 1/6, right? So this is going to be 1 kilogram times 1/6 of a meter squared. Yeah? 1/6 because this is a third. We're cutting that in half, so that's a sixth. That's why they wanted it to be 6 meters long. But that's okay, because we're going to do it 1 meter. It's okay.
I see, that's what.
It's okay. Mayo Winty, we got it. Okay. All right, we're going to do this one. Let's do it. What's the mass of the second piece? 2m, or in this case, 2 kilograms. It's all good. And what's the radius for this one?
3/6.
Which is what?
1/2.
Ding, ding. You got it. Are we okay so far? So we're really just adding up. If it was just this piece, it's going to rotate here. If it's this piece here, that part's going to rotate here, which is 1/2 meter away from the axis. And then piece number 3. We're going to add another, how many kilograms is that one? 3 kilograms. And how far away from the axis of rotation is that center of mass? 5/6 squared. So if you have a calculator, you can get it out and do that. Sure thing. What is that total moment of inertia about the left side? So get out a calculator, friends, because you're going to need one soon anyway. Get out a calculator. Go, go, go. Oh, dear. We doing okay? Do you need a calculator? Anybody else need a calculator? Yes, of course. Gunnar, was that you saying here, please?
Do you need to have one or 36?
I have. Anybody else need a calculator?
2 and 18. You guys get 2 and 18.
If you have your calculator set for mixed numbers.
Because why not? How do we do?
That's Jasmine. Jasmine likes mixed numbers. Mixed numbers are 2.6.
Yeah, it's your thing. Did you get a total?
Yes.
What'd you get?
2.6.
Repeating? We'll just call it 2.6. 2.61? We'll call it good. What are the units? Don't overthink it. Kilogram meter squared. So, we have something to quantify this. Now, before we do the other math, which I want to do because I want to actually see how different they are, let's imagine what we're talking about here. So we've got most of the mass of this whole thing really far from or really close to the axis of rotation? Far from. If we have something that's far from the axis of rotation, is that going to make it easier or harder to stop it? Harder to stop it. The bigger the moment of inertia, the harder it is to stop this thing from rotating or start it rotating. Does that make sense? So therefore, I'm thinking this is going to be right. I'm thinking that the moment of inertia about the left end is going to be greater than about the right end. But let's do the math right now to figure it out. Can you set this up, this statement up about the other end, about the right end?
Isn't there a simpler way to do it?
There are always simpler ways to do things, but I want to go through this because I know what problem I'm going to give you next. Do you want to talk about the simpler way to do it?
Yeah.
No, just try it. No, let's just do it.
I mean, go ahead, Gunnar, go ahead.
Okay, well, because what you can do is you can just set the center of mass,
Mhm.
the whole thing, and use that radius.
Right here?
Yeah.
For sure you can. The next thing that we're going to do, you're right, and that would have been a simpler way. The reason that I did it this way was because I know what's coming next, and I was kind of gearing you guys up for that. But I appreciate yes, indeed, you are correct. Yeah. So I apologize. So you can do the other one that way. That'll be easy. Either way, whichever you want to do it, but go ahead and do it. I just had it in my head the other way because I was thinking about the next one. So set it up. Either way, you can do it my way or you can do it Gunner's way. They're both good. All right. So, to reiterate here. Henry, have we changed sticks?
Yeah. We have the same stick.
It's the same one, right? Same one, but it's rotating about the other axis to the other end. So here, most of the mass is way far away. If most of the mass is way far away, it's going to be really hard to speed it up or slow it down. Doesn't matter which one. Okay? If I put the axis of rotation over here by the 3m side, on this side over here, now it's almost the same expression, but what changes?
The ones, 5, 6.
This thing and this
It's
thing.
on freeze, man.
Oh, it's on freeze! Rats! There you go. Is that better? Thanks for letting me know. Okay?
Oh my goodness.
And what do you get for the total now?
You get 1 and 5/18.
Oh my gosh.
1.27.
1.3-ish.
1.27.
Yeah.
Okay. How are we doing, team? Question, go.
Is that just the unit for moment of inertia?
Yeah, it's kind of unexciting, isn't it? Yeah. I'm sure that somebody's like made something else up, but this is just what we always use. All right. Are you ready for more?
Yeah.
Okay. Now, Henry, I hope this one doesn't blow your mind because it's not just a stick. It's like a, did you guys ever, I don't know if you remember this from when you were a kid. Do you remember jacks?
Oh, yeah.
Those little things that like you leave on the floor and then your parent steps on and then they say things that we're not allowed to repeat in school, like that kind of thing?
Like
Right? Those little like pointy things. So I got you like a little thing that looks like that.
Why do those exist?
Just to make parents crazy. I don't know. No, you bounce the ball and then you pick them up. I'll teach you sometime. It's kind of fun, I guess. I don't know.
Is that what they used to do in high school?
Is that what we were supposed to do? I just drew it.
All right. So take a look over here, friends. We've got, so, thank you. 6 small brass and aluminum spheres are connected by 3 stiff, lightweight rods to form a grid, a rigid object shaped like a jack. So that's literally why I asked you if you knew what a jack was, right? So it's just an X, Y, and Z coordinate plane. Okay, that would be like the theoretical version. A jack would be like the, physical version of that. Okay, so you got these different spheres that are all attached. The sticks are very lightweight, which means that we don't need to worry about the moment of inertia of them. Okay, we don't care about that. It says the rods are joined at their centers and they're mutually perpendicular and they lie along the axis of a coordinate system. I just said that, I suppose. All of the spheres are the same distance from the connection point of the 3 rods at the origin of the coordinate axis. The brass spheres are shaded and are identical. Okay? The aluminum spheres are identical and have less mass than the brass spheres. And they're unshaded. Ignore the mass of the rods. Now, this says, rank the moment of inertia of each of these about the x-axis. So that means that if I am going to, this is going to be a thinker question, my friends. If I rotate it about this axis right here, we're going to rank the moment of inertia. This is why in the last question I was like, let's just add them up. Because in this one, we just add them up. And this is the one I was like thinking about. I was like excited to do this question. I kind of forgot about the other one. So, okay. I'm going to let you work on this. Talk to your table mates. I'll give you a couple minutes and then we'll discuss it. Sound good? Question first?
Sorry, what are the gray dots?
The gray ones are more massive. Or hold on. Brass spheres are shaded.
Yes, C equals B. Yeah, I was like, why is C bigger?
So the brass spheres have more mass.
Oh, yeah.
Yeah. The aluminum ones have less mass. All right. Get started, friends. Okay. Made decision. All right, show me your boards.
Show me your board.
They're the same distance.
D, B, C, A, D, B, C, C, B. You guys like to always do things in non-alphabetical order when they're equal. All right.
DCB makes more sense than
I suppose that's true. I suppose that's true.
No.
All right. Life is good?
Can we go over it?
Yeah, for sure. Friends, can I have your attention up here? Yes, let's go over it.
Okay.
Do you want to get us started?
Well,
I will start it.
No, Courtney's going to start. You can go in a minute.
well, I kind of was super confused, and then I realized that everybody was done, so it was probably easier than I thought.
Okay.
So
That's a good way to start.
D has the most steel balls. So
Brass.
brass.
Yeah, but that's okay.
So it would be. So it's the largest.
Okay. So if we find the total, right? Like, let's do it one at a time. So you got 1, 2, 3, 4. Each of those has a mass that's the same. And these radii are all the same, right? So you've got 4 of mr squared. They're all the same. Yeah? Okay. So the mass of the, what did we say, brass?
Yeah.
Okay. Now, do I keep talking?
Well, and then I knew that A was the littlest.
Why?
Because it has 4 aluminum spheres.
Mm-hmm.
And,
That's what they are.
Yeah.
Oops, yeah, okay, that's right. Okay.
And yeah, so their mass is less.
Okay.
And then, well, I now know that B and C are equal because they have the same amount of, like, it's 2 and 2.
Yep.
At first I didn't think that, but I got it.
Cool.
So good for B.
Go you. This is your unit, Courtney. We know this is true, right? So they're 2 and 2, and it's all good. It's just like this one has rotated 90 degrees about this axis from this one, right? That's all it is. And the orientation at any given moment does not matter. It's just about the distribution of that mass. That's it. Sweet. All right. Answer that question. So now instead of going about the x-axis, we're going to do the same as we're going to do the y-axis. Same answer? Do you need to erase or no? I don't know. You figure it out.
Yeah, you are. It's DCB.
If you need to fix it, fix it. Otherwise, I'm going to ask how much for your boards up in just a minute. What?
You just have to change the equal sign. Don't worry about it. Don't worry about it. Yeah, you just make it, it's the same. Just change the equal sign.
D.
Why did you change where the C was?
All right, friends, show me your boards. Can't read upside down.
You guys did it obvious.
Yeah, we definitely did. It's because it's.
And you don't want to hold your board up? Or you just... Oh, okay, gotcha. Okay. All right, so I was told that if I had written this in the right order, I could have just changed my equal signs. I don't know if that's right, though. Let's double check. So oops, I'm still frozen. I don't know why I do that. Okay, anyway. So now I'm orbiting, rotating about,
Yes, too, I'm orbiting.
friends, about this blue axis, this y-axis. Does the moment of inertia change depending on which axis I'm rotating around?
Yeah.
X, Y, or Z?
Yeah.
Yeah.
You're orbiting around.
For D?
Oh, for D.
Oh,
No.
not for D. Not
No.
for D.
No.
For C?
Yes.
For B?
Yep.
Yes.
And A?
Yes.
For sure. Yeah. These two both have 2 brass and 2 aluminum. Right? This one has 4 brass, as does this one. Yeah. Cool. Good for you guys. All right. There's always more. I know, right?
I could probably do Z.
I was going to give you a whole different problem. You could probably do Z. Do you want to do Z real quick or no? Okay. All right, here's the situation. Abstract art. I don't know if any of you are artists, abstract artists, or if you know people that are. Your friend is creating an abstract sculpture that consists of 3 small heavy spheres that are attached by lightweight 10 centimeter long rods as shown. The spheres have masses of 1, 1.5, and 1 kilograms respectively. Okay? It asks, what is the moment of inertia if this object is rotated about this axis of rotation? Okay? This axis of rotation where we're going around this way. Okay? In part B, same situation, but now we're spinning it this way. Okay? Same sculpture, just 2 different axes of rotation. I'm going to ask you to do just part A first. Let's get part A, make sure we understand it, and then we'll move on to part B. Okay? Absolutely. Feel free to talk to each other. Add it up. This is, again, why, while Gunner's answer was simpler in the other one, we wanted to add them up. So we're going to add them up here. Go for it, friends. All right, how do we do with part A? Did you get an answer?
250 kilograms per centimeter squared.
What did you get? I'm sorry.
250 kilograms per centimeter squared.
Bless you. Bless you again. Holy cow. Oops. You can't see it. I wrote it down. There you go. 250 kilograms centimeter squared. Do you guys agree with that? I want to make sure you do. And if you don't, then let's figure it out. Okay. So I total is going to be, I'm just going to write this down, write it out totally. So I1 plus I2 plus I3. So that's going to be mass 1 times radius 1 squared, mass 2, radius 2 squared, mass 3, radius 3 squared. The radius for 1 is 0, so that goes away. That's nice. So then we've got a mass of, 1.5? Times the radius is 10 centimeters. Is that okay?
No, that's where I went wrong.
Okay.
So I thought,
Go ahead, I'm listening.
because in that block problem we did,
Yeah.
right, we took half of its length, right? Is that because we were going to like the center of mass?
Yes.
Yes.
So because these sticks are nearly massless,
Okay.
we don't need to worry about the moment of inertia of them. All we care about are the 3 spheres.
Their centers of mass.
And their center of mass is in the center of the sphere.
So, okay. So you only have to do that if they're like weird objects or something?
Yes. Yes. Welcome to Monday. It'll be great.
Yeah.
There you go. It's time to go. Please make sure that the whiteboards get put back. You don't actually have technically any homework this weekend, but I'd make sure that you get caught up if you're not there yet. Not implying that you haven't done your homework.